In 10.3, we are simplifying radical expressions. And so for exercises 1 through 6, we want to use the multiplication property of radicals to simplify these expressions, assuming the variables represent real numbers. So the square root of 24, if you were to type that into your calculator, first of all, that's what I try to do first. I always try to type these into my calculator. If it doesn't give you a pretty number, if it gives you like a decimal, then you may need to look at that radical, and you could simplify it and rewrite it. So the square root of 24, we want to look at 24, and you can draw a factor tree of it. Let's see, 24 is 2 times 12, and 12 is 2 times 6, but 6 is 2 times 3. So the square root of 24 is really 2 times 2 times 2 times 3. The square root of 2 times 2 times 2 times 3. And if you'll look, there is a group of 2. And if you have a group of 2, you can pull that out. And what is left in there, you just multiply together. So the square root of 24 we could rewrite as 2 square roots of 6. Now, I do want to talk about this group of 2 really quickly. It's not a group of the number 2. I mean, it is in this case, but a group of 2 things that repeat twice. With a square root, think about the index right here being 2. That's how many times you're looking for something to repeat twice. And these 2's right here repeated twice. The 2 and the 3 right here did not repeat. They were left over, so they stayed. I sometimes call this jail. They stayed in jail, but this group of 2 was freed. Okay, it went on the outside of that radical. Let's try the next one. Okay, so we have 40. Now 3, I'm going to kind of do some scratch work down here. 3 is already on the outside of the radical, but 40, let's draw a factor tree really quickly. 40 is 2 times 20. 20 is 2 times 10. 10 is 5 times 2. So the square root of 40 could be rewritten as 2 times 2 times 2 times 5. I don't have to put those numbers in any certain order. And the way I divide out 40 doesn't matter either. I could have said 40 is 8 times 5, and 8 is 2 times 4, and 4 is 2 times 2. And what I end up writing back underneath that square root is what is on the end of one of these picks, or the end of one of these forks that doesn't fork out again. So 5 is on the end of a fork. 2 is on the end of the fork. 4 was, but it forks out again. So 2 and 2. 5, 2, 2, and 2 is what went on the inside of that radical. So we're looking for a group of 2 things that repeat. 2 and 2 repeats. It doesn't matter which one you should select. You can select that one, or you can select these 2. It really doesn't matter. But whichever 2 you visualize, whichever group of 2 you visualize, bring it out and put what is left over back inside of the radical. So this gives us a final answer of 6 square roots of 10. So that 3 that was outside in the very beginning just gets multiplied by whatever comes out in front of the radical. So this one it is a little different. But when we're taking the root of a number versus the root of a variable, it's different. So in the last section, we did things like the square root of c to the 12th, which would have been how many times does the index of 2 that isn't written right there 2, again, it's understood 2 when we don't have a number written right here. So this is the square root. How many times does the index of 2 go into 12? Well, it goes into 12 6 times evenly. So that would be an answer of c to the 6th. Or if I had the cubed root of c to the 12th, I would say, how many times does 3 go into 12? And it goes into there 4 times evenly. The reason being for these answers, c to the 12th is really c written out 12 times, and if you write it out 12 times and multiply it by itself 12 times, there are 6 groups of 2. And then when we decide to look closer at that cubed root of c to the 12th, and we get c to the 4th as our answer, if you write c out 12 times again, but this time you're looking for groups of 3 instead because it's the cubed root, then you have let's see, 1 2 3 1 2 3. You have 4 groups of 3. Okay, so let's focus on the cubed root of c, excuse me, not the cubed root, but the square root of c to the 12th. So we're going to draw out, not c to the 12th, c to the 13th. We're going to draw out 13 c's this time. I just drew them all side by side. C to the 13th means literally to write that out, multiply by itself 13 times. And so with this being a what root? It's a squared root because there's no index written right there. We're looking for a group of 2. So 1 group of 2, 2 groups of 2, 3, 4, 5, 6, and 1 left over. 1 left over right here. Okay, so what these groups of 2 that I've circled means is that there are 6 groups of 2. So c to the 6th comes out, and whatever didn't repeat twice, whatever is left over, stays in jail. So it goes inside of the radical. So basically, leftovers are going inside the radical, stays in jail. Leftovers go in the trash, whatever way you want to think about it. Okay, so with this one, I'm going to do some scratch work down here. I'm going to draw me a square root. I already know that -4 is coming out in front of the square root because it already was. And so I have the square root of k to the 7th and the square root of L to the 10th. Okay, so k to the 7th, the index with that square root again is 2. Okay, so how many times does 2 go into 7? It goes into there 2 times 3 is 6. So it goes in there 3 times with 1 left over. We can visualize that by writing k to the 7th out. And we're looking for groups of 2. You can see that there's 3 groups of 2. So k cubed, 3 groups of 2 with 1 left over. And then L to the 10th, remember that index is 2. And 2 goes into 10 5 times evenly. My L is a little wonky, I'm sorry about that. Evenly with none left over. So the square root of k is the only thing, left inside that root. L didn't have any because, let me write these L's. There are 5 groups of 2 and none left over. So only the leftovers go inside that radical. For a final answer of exactly what I had written here, but made it look a little nicer. Okay, so for this one, I'm going to draw on number 5 some scratch work here at the bottom. I already know I have a 5 that's going to be on the outside, okay? And then I want to think separately about the square root of 48 and the square root of c to the 7th. So 48, type it into your calculator. See if there's a square root of 48. There isn't one. So let's draw that factor tree. 48, 2 times 24. 3 times 8. 8 is 2 times 4, and 4 is 2 times 2. So write down everything that is on the end of one of these sticks that doesn't stick out again. So the square root of 48 could also be written as, let's see, 1, 2, 3, 4 2's. 2 times 2 times 2 times 2, and a 3. So with a squared root, you're looking for something that repeats twice. So a 2 comes out and a 2 comes out. And then this 3 right here didn't repeat twice, but it still matters. You just don't, get rid of it. It didn't repeat, so it just goes back to jail, back to the radical, okay? And then c to the 7th, you can write out 7 c's if we need to. 1, 2, 3, 4, 5, 6, 7. Or you could just say, okay, this index of 2 right here, how many times does 2 go into 7? It goes into there 2 times 6. 2 times 3 is 6. So it goes into there 3 times with 1 left over. And we can see that if we decide to circle the groups of 2. So our final answer here, 5 times 2 is 10 times 2 is 20 c cubed square roots of 3c. So I'm going to continue on sort of just drawing me some scratch work from the beginning, so that a negative comes down. We have the square root of 50, the square root of a to the 5th, the square root of b to the 8th. 50 is 5 times 10, and 10 is 2 times 5. So 50 can be rewritten as 2 times 5 times 5. So there is a group of 2 5s, so a 5 can come out, and the number 2 stays in because it was left over, it did not repeat twice. And a to the 5th, we can again say that 2 goes into 5 4 times with, 2 goes into 5 twice, because 2 times 2 is 4, twice with 1 left over, and we may need to visualize that a 5 times. So 2 groups of 2, 1 left over. And b to the 8th, 2 goes into 8 4 times, and no more left over. And we can visualize that. If we draw 8 b's, there are 4 groups of 2. So our final answer is negative 5a squared b to the 4th square roots of 2a. So let's look at some more examples. This is using order of operations if necessary to simplify the expression. So before I start saying that the square root of d to the 13th is equal to d to the, 2 goes into 13, 6 times with 1 left over. But before I start doing that, let's see if we can simplify the inside. Let's see if we can simplify the inside first. D to the 13th divided by d to the 5th is d to the 8th, because what you do, see, it's the same base, and when you're dividing, you subtract the bases. So 13 minus 5 is d to the 8th. Now that it's d to the 8th, how many times does 2 go into 8? It goes into there 4 times. So nothing is left inside of the radical. The d to the 4th came out, because there, if you wrote out 8 d's, there's 4 groups of 2. So d to the 4th is our final answer right there. On number 8, the square root of 10 over 90, this would be best if we simplified that fraction first. 10 divided by 90 is 1 over 9 if you simplify that fraction. And then we can say, okay, well, that's the square root of 1 divided by the square root of 9. And the square root of 1 is 1, and the square root of 9 is 3. On number 9, we can see if we can simplify what 72 divided by 2 is, and it is 36. And then with the g, we can keep the base and subtract the exponents. The exponents are 9 and 1. So you don't have to write it like this. I didn't write it like that last time. But that would be the square root of 36, g to the 8th. And now think about the square root of 36 and then think about the square root of g to the 8th. The square root of 36 is 6. And the square root of g to the 8th, 2 goes into 8 4 times evenly. So on number 10, you can't do anything with the inside of the root and 27, but you can with 3 and 27. What I'm saying is now 18 over 27, 3 goes into both of those numbers. However, 18 is trapped inside the square root, so I'm saying you can't touch it right now. But 3 and 27, the fraction 3 over 27 would simplify into 1 over 9, and then you just have the square root of 18 out beside it. The square root of 18, type that in your calculator. You find out that there is no square root of 18, but let's just see if the square root of 18 can simplify. Let's do a factor tree on the number 18 really quickly. 18 is 2 times 9, and 9 is 3 times 3. So the square root of 18, it would be equal to the square root of 2 times 3 times 3. There's a group of 2 3's. So a 3 can come out, and the 2 stays on the inside. And now 3 times 1/9 is 1/3. As we're moving on to number 11, I want to make sure that we see the difference between the problems at number 10 and number 11. On number 10, you have 3 times 8 square root of 18 divided by 27. Right here, you have an addition problem. You have -2, not times, but plus the square root of 100. So I can't just say -2 divided by 4 is a half. Now, I can separate it if I need to. I can say -2 over 4 plus the square root of 100 over 4 equals, that's going to be -1/2, plus the square root of 100 is 10. 10 over 4 is equal to 5 over 2. So we can say -1 plus 5 over 2 equals 4 over 2, which then simplifies. 4 divided by 2 is equal to the number 2. On number 12, I want to show you this application problem, really from geometry, in order to find this side right here, because what we're going to end up getting is a radical that we have to simplify. But let's focus on getting that radical first, and that's where the geometry comes in. The Pythagorean theorem states that a squared plus b squared equals c squared. So this is your sides, your legs, and this is your hypotenuse, which is 9. So I know that 6 squared plus b squared equals 9 squared. I don't know what b is, okay? So let's see, 36 plus b squared equals 81. So b squared equals 81 minus 36, and we get 45. But I don't want b squared, I want b. So b squared is equal to 45, so b would be the square root of 45. Well, what is the square root of 45? You type it in the calculator, you don't get a pretty number. So let's see if we can at least simplify the radical. 45 is, let's see, 5 times 9. 5 is prime, 9 is not, 9 is 3 times 3. So you could rewrite the square root of 45 as the square root of 5 times 3 times 3. The 3's can come out, or a 3 can come out because the 3's repeated, and the square root of 5 did not repeat, so it stays inside. So instead of doing square roots, we're working on cubed roots right now. We have the cubed root of 54 and the cubed root of x cubed. Well, remember when, let's work on the variable first. Remember when we were taking the squared root of a variable and the index was 2 that you didn't see, and you had to say how many times does 2 go into the power? Well, now the index is not 2, the index is 3. So how many times does 3 go into 3? 1 time. And it doesn't, a variable isn't left in the radical. Another way you could think of the cubed root of 3 is, or excuse me, cubed root of x cubed is the cubed root of x times x times x. And you're looking for a group of not 2 this time, but a group of 3 things that repeat. Why 3? Because it's the cubed root. Okay, so we've gotten that knowledge. Let's look at 54. Is there a cubed root of 54? You type that in the calculator, and there's not. You get a decimal. So let's see if we can simplify that radical. 54, let's write the prime factors. 54, you could say 2 times 27, and 27 is 3 times 9, and 9 is 3 times 3. So the cubed root of 54 would equal the cubed root of 2 times 3 times 3 times 3. So is there a group of 3 things that repeat? Yes, there are. That 3 comes out, and whatever doesn't repeat 3 times stays in. So 3x cubed roots of 2. Looking at the cubed root of 250 divided by 2, I can actually simplify the inside of that radical first. 250 divided by 2 is the cubed root of 125. And you type the cubed root of 125 in the calculator, and you get a pretty answer. 5. That's also because 125 is 5 times 5 times 5. There's a group of 3 things that repeat. Nothing is left over, so there's no radical. There's nothing left in the radical. Okay, on number 15, we have the cubed root of z to the 8th divided by z squared, and I can, again, simplify the inside on this one. Z to the 8th divided by z squared. Keep the base, subtract your exponents. So that's equal to z to the 6th, and we're looking to see, and excuse me, I didn't draw my index of 3. We're looking to see how many times this index of 3 goes into the power. And so 3 goes into 6 2 times evenly. Nothing's left over. No need for a radical. Okay, let's look at the last 2 exercises. On number 16, I can simplify what's inside of these parentheses. -1 minus 5 is -6. And 1 plus 1 is 2. Well, let's go a step further. -6 squared. Be careful. In some calculators that you type this in, reads it like this, and that would only square the 6 and not the negative. So if you're going to type that in the calculator, I would put it in parentheses. But negative 6 times negative 6 is positive 36, and 2 squared is 4. So we're essentially looking at the square root of 40. There is no square root of 40, but can we simplify that radical? So 40 is 2 times 20, and 20 is 2 times 10, and 10 is 2 times 5. So this is the square root of 40 is equal to the square root of 2 times 2 times 2 times 5. And what repeats, now we just got through doing a few cubed roots, so we're back to a squared root. So our index is 2. We're looking for something that repeats twice. So the number 2 repeats twice, meaning a 2 can come out, and whatever is left over, in this case 2 and 5, stays in the radical. So the answer would be 2 square roots of 10. Be careful of writing this as 2 square roots of 25. Make sure that you got that visible multiplication dot right there, and that we multiply whatever is left together to get, in this case, 10. And then on number 17, we can factor this trinomial. The factors of 4, the factors that multiply to give me 4, but add to give me 4. So factors of 4 are 1 times 4 and 2 times 2. 2 times 2 also adds to give me 4. 2 plus 2 also adds to give me 4. So I can write this as x plus 2 times x plus 2. Well, when you multiply something by itself, that's the same thing as squaring it, right? Okay. The squared root undoes the square. Technically, we're supposed to put this in absolute value bars, but we do not need them because we know that the variables represent positive real numbers. So we can write our answer as x plus 2.